everyone, I am Princess Abigail.
I am Janice.
And I am Maiden.
Welcome to our video on brute force algorithms. Today, we'll dive into what brute force algorithms are, how they work, and why they're important in problem solving. Objective statements. Here's what we'll cover. First, definition and basic of brute force algorithms. Second, example problem of brute force algorithm. Third, optimization techniques. Lastly, strength and weaknesses of brute force. By the end of this video, you'll understand how they work, where they are used, and how to implement them yourself. Brute force algorithm is a simple and straightforward approach to solve a problem by trying every possible solution until finding the best one. It typically involves systematically checking all possible solutions without employing any optimization techniques. In computer science, brute force search for exhaustive search, also known as generate and test, is a very general problem-solving technique and algorithmic paradigm that consists of systematically checking all possible candidates for whether or not each candidate satisfies the problem statement. Brute force algorithms are applicable in various problem domains, including searching, sorting, optimization, and combinatorial problems. They are often used when the problem size is small or when more efficient algorithms are unnecessary due to the manageable search space. In the realm of algorithmic problem solving, brute force techniques represent a straightforward approach where every conceivable solution within the problem space is exhaustively tested until the correct one is discovered. This method involves systematically exploring all possible combinations or permutations until the desired outcome is achieved. However, while brute force algorithms guarantee correctness by leaving no stone unturned, they often come with a trade-off in terms of efficiency. The time complexity of such algorithms, a crucial metric in algorithm analysis, quantifies how the algorithm's runtime scales with respect to the size of its input. This time complexity is frequently expressed using Big O notation, a mathematical notation that provides an upper bound on the growth rate of the algorithm's runtime as the input size increases. Essentially, Big O notation offers a standardized way to describe the worst-case scenario for the algorithm's performance, indicating how quickly algorithm's execution time increases relative to the size of the problem it's solving. By understanding the time complexity of a brute force algorithm, developers and engineers can gain insights into its efficiency and scalability, helping them make informed decisions about algorithm selection and optimization strategies. Thus, while brute force algorithms offer simplicity and correctness, their feasibility for a large-scale problems hinges on managing their exponential time complexity and exploring alternative, more efficient approaches when necessary.
In this simple problem, we need to find the maximum number. So the given numbers are 314 up to 535, and the max element is equal to 3. Now, let's compare these given numbers to find the maximum number. Let's start to compare the max element to the first element in iteration. Since 3 is not greater than 3, max element remains 3. So in result, there is no change. Next, since 1 is not greater than 3, max element remains 3. As a result, there is no change. Next, since 4 is greater than 3, so our max element updates to 4. As a result, the max element is updated to 4. Next, since 1 is not greater than 4, max elements remains 4. As a result, there is no change. Then, since 5 is greater than 4, our max element updates to 5. As a result, the max element is updated to 5. Let's proceed. Since 9 is greater than 5, our max element updates to 9. As a result, the max element is updated to 9. Next, since 2 is not greater than 9, max element remains 9. As a result, there is no change. So let's proceed until we find the max element. In the last iteration, since 5 is not greater than 9, so the max element remains 9. As final result, there is no change, and our maximum value is 9. After completing the iteration through all elements in the list, the maximum value found is 9. After completing the iteration through all elements in the list, the maximum value found is in the method. The analyst systematically tries every possible combination of the characters until the correct password is found. If the password consists of 4 characters, and each character could be any lowercase letter A to Z, the brute force algorithm will start by trying 4A, then AAAB, AAAC, and so on, until it finally arrives at 4Z. While this method can be time-consuming, especially for longer passwords or more complex character sets, it guarantees success eventually. For another example, let's use letters for the maximum character. Let's consider a brute force algorithm for finding the maximum character in a list of characters. The process involves iterating through each character and keeping track of the largest character. Start by assuming the first character by is the maximum. Set max char to letters, which is D. Compare each subsequent characters with max char and update max char if a larger character is found. So first, let's compare the first letter, which is A, with max char D. Since A is not greater than D, max char remains D. As a result, there is no change. Max chars remains D. Then let's compare the second letter, which is C, with max char D. Since C is not greater than D, max char remains D. As a result, there is no change. Max char remains D. Then compare the third letter, which is F, with max char D. Since F is greater than D, update max char to F. As a result, the max char is updated to F. Next, compare the fourth letter, which is B, with max char F. Since B is not greater than F, max char remains F. As a result, there is no change. Max char remains F. For the fifth letter, compare E with max char F. Since E is not greater than F, max char remains F. As a result, there is no change. Max char remains F. For sixth letter, compare G with max char F. Since G is greater than F, update max char to G. As a result, the max char is updated to G. Next, for the seventh letter, compare H with max char G. Since H is greater than G, update max char to H. As a result, the max char is updated to H. Then compare for the eighth letter, which is A, with max char H. Since A is not greater than H, max char remains H. As a result, there is no change. Max char remains H. And last, compare the ninth letter, which is B, with max char H. Since B is not greater than H, max char remains H. As a result, there is no change. Max char remains H. After iterating through all characters in the list, the maximum character found is H. This process demonstrates how the brute force algorithm checks each character in the list and updates the maximum character with a large character is found.
There are ways to optimize brute force algorithm. First is pruning eliminate parts of the search space that don't need to be explored. Pruning in the context of brute force algorithms involves strategically discarding certain branches or possibilities within the search space that are deemed unnecessary or irrelevant to finding the solution. By identifying and eliminating these unproductive paths
execution, pruning significantly reduces the computational burden and accelerates the search process. This optimization technique ensures that the algorithm focuses its resources only on the most promising areas of the search space, ultimately improving efficiency and performance. Second, heuristics. Use heuristics to guide the search process. Heuristics in the context of brute force algorithms refer to the use of rules, strategies, or guidelines to guide the search process towards potentially promising areas of the solution space. Unlike exhaustive search methods, which consider every possible solution, heuristics offer a more targeted approach by prioritizing certain paths based on predefined criteria. By breaking down the problem into independent or loosely coupled components that can be solved simultaneously, parallel processing exploits the potential for parallelism inherent in the problem, leading to significant improvements in execution, speed, and overall efficiency. This approach is particularly beneficial for brute force algorithms dealing with large datasets or complex computations, as it allows for more efficient utilization of computational resources and faster solution discovery. Second, they can be time-consuming and impractical for problems with many possible solutions. Brute force algorithms exhaustively evaluate possible solutions to a problem, making them increasingly time-consuming as the number of potential solutions grows. Consequently, for problems with a vast solution space, such as combinatorial optimization or password cracking with long password, brute force approaches become impractical due to the sheer computational resources required. By leveraging domain-specific knowledge or patterns observed in the problem space, heuristics help the algorithm focus its efforts on areas more likely to lead to the desired solution. This selective exploration often leads to faster convergence and improved efficiency in finding solutions, especially in complex problem domains where exhaustive search is impractical. And last, parallel processing split the problem into smaller sub-problems that can be solved simultaneously. Parallel processing involves dividing a problem into smaller, more manageable sub-problems and solving them concurrently using multiple processing units or threads. Instead of tackling the entire problem sequentially, parallel processing harnesses the power of parallel computing to distribute the workload across multiple processors or cores, thereby accelerating the overall computation. Algorithm strength. Brute force search is effective for exploring large solution spaces and finding solutions, as illustrated by Katia. It excels at quickly identifying programs made of multiple function applications, even when using a versatile library. Furthermore, it efficiently assesses the number of possible functions that match a given type, offering baseline performance data for comparison with other techniques like genetic programming. Limitations and challenges. Brute force techniques are particularly useful in coding challenges, especially when the problem scope is limited and efficiency is not a primary concern. These methods involve exhaustively searching through all possible solutions to find the correct one, making them straightforward to implement and often guaranteeing a solution if one exists. For small-scale problems or preliminary stages of problem solving, brute force can be an effective and reliable approach, allowing developers to quickly test hypotheses or establish baseline results. However, the major drawbacks of brute force techniques lie in their inefficiency and high computational cost. As the size of the dataset or the complexity of the problem increases, the time and resources required for brute force methods can
can become prohibitively large. This inefficiency makes brute force impractical for solving large-scale or highly complex problems, where more sophisticated and optimized algorithms are necessary. However, the major drawbacks of brute force techniques lie in their inefficiency and high computational cost. As the size of the dataset or the complexity of the problem increases, the time and resources required for brute force methods can become prohibitively large. This inefficiency makes brute force impractical for solving large-scale or highly complex problems, where more sophisticated and optimized algorithms are necessary. The exponential growth in potential solutions can lead to significant performance issues, highlighting the need for alternative approaches in scenarios demanding high efficiency and scalability. Comparative analysis. Brute force is a straightforward method used in algorithmic problem solving that involves systematically checking every possible solution until the correct one is found. This approach does not rely on any shortcuts or heuristics. Instead, it exhaustively explores all potential solutions in a methodical manner. By evaluating each option one by one, brute force ensures that the solution will be found if it exists within the given search space. This makes it a reliable but often time-consuming method, especially for large or complex problems. Brute force algorithms function by sequentially searching through each element until the desired result is identified or all options are exhausted. For instance, in a brute force string matching algorithm, every possible position in the text is checked to see if the pattern matches. Similarly, in a brute force search for the maximum value in a list, each element is compared to find the largest one. While brute force algorithms are simple to implement and understand, their performance can be poor for large datasets due to their exhaustive nature, making them less efficient compared to more optimized algorithms.
However, they also have significant weaknesses. First, they are inefficient for large datasets due to high computational complexity. Computational complexity measures the amount of resources required by an algorithm to run, typically in terms of time, how long it takes, and space, how much memory it uses. For brute force algorithms, this complexity often grows exponentially within the size of the input. Second, they guarantee a solution if one exists. Brute force algorithms methodically evaluate every possible solution within a given problem space, ensuring that if a solution exists, it will eventually be found. This exhaustive search approach leaves no stone unturned, providing a guarantee that the algorithm will succeed in identifying the correct solution if it is indeed present within the problem's constraints. Strengths and weaknesses. Brute force algorithms have some key strengths. First, they are simple and easy to implement. Brute force algorithms are straightforward in their approach, often requiring minimal complexity in their implementation. They involve iterating through all possible solutions systematically, making them accessible even to those with basic programming skills. This simplicity facilitates quick implementation and understanding, making brute force algorithms an attractive option for tackling various problem-solving tasks.
Second, they can be time-consuming and impractical for problems with many possible solutions. Brute force algorithms exhaustively evaluate all possible solutions to a problem, making them increasingly time-consuming as the number of potential solutions grows. Consequently, for problems with a vast solution space, such as combinatorial optimization or password cracking with long password, brute force approaches become impractical difficult due to the sheer computational resources required.